Okay, welcome to a video on how objects acquire charge and just the nature of charge in general. We spent the last video talking about electric charge, and actually that was more of a nature of charge video. One of the things that we talked about was we discussed how electric charges move around, or specifically we discussed what type of objects or electric charges move around. Typically, only negative charges, which we usually call electrons. Okay, there are other negative charges besides electrons, but we're thinking of electrons here, the things that are on the outside of the nucleus in an atom. Typically, only those move. The positive charges, which are typically, in most cases, protons, they do not. They are locked in the nucleus, okay? They are bound very tightly to the nucleus. They don't get away. Every once in a while, you can see a stray proton flying around, but it's not that often. So, when I say that electrons can move around, there's varying degrees to this. Some objects allow electrons to move around wherever they want to go in the object, or even get, taken away from the object very easily. Objects that allow electrons to move around fairly freely are called conductors. The best conductors are usually metals, as you probably know. This is some review from maybe earth science or middle school physical science. In a conductor, electrons will spread out as much as possible. The reason that they spread out is because remember that how charges interact with each other. Like charges repel each other, opposite charges attract each other. If you have a whole bunch of electrons in a conductor, then what's going to happen is they're going to repel each other so that they all spread out so that they can be as far away from each other as possible. Let me draw you a little before and after picture here. Let's say that you have a conducting sphere, a metal conducting sphere. And initially, you put a whole bunch of electrons on it. Electrons are symbolized by these minus signs. 10 in total. The number doesn't matter, but it's going to be important for later on. If you let those charges go, if you let them do their thing, then they are going to repel each other. If this sphere is isolated, meaning they can't leave the sphere and no more can join them, the charges are going to spread out. They will repel each other so that eventually they all kind of settle as far away from each other as possible, like so. So they spread out and they go to the surface of the conductor. On the other hand, we have conductors where charges can move around very easily. We also have insulators. Insulators are materials that impede or tend to halt the free movement of electrons. A few good insulators are rubber, wood, and actually air. Charges are not good at moving through air. Another good conductor, by the way, are some liquids such as water, especially if it has ions in it, freely floating ions. All objects, whether it's a conductor or an insulator, have the ability to become polarized. And objects get polarized when electrons move around inside of an object. However, even though they're moving around inside the object, that does not mean any charges actually leave the object. Here's an example of polarization that you've probably seen. Let's say that you have a balloon, a negatively charged balloon. Balloons are actually usually charged negatively just because of how they're made. We know it's negative because it has these extra negatives floating around. And it comes up near this metal wall. We're going to say that the metal wall is initially neutral, and the way that we're going to show that is equal numbers of positive and negative charges. Okay, so the balloon is going to approach that metal wall, and here's what's going to happen. The balloon is negatively charged. The wall, a metal, is a conductor. Because the wall is a conductor, the charges on the metal wall, at least the negative ones, they can move around a little bit. So what's going to happen, those negatives that are on this surface of the wall are going to say, wait a sec, we don't want to be near these electrons, we're getting repelled away from them. Those negatives are going to go to the other side. The positives are locked in place, remember, positive charges don't really move around a lot. But the negatives get pushed to the opposite side. So look at what happens here. This means that the wall itself is now polarized. A polarized object kind of has a more positive side and a more negative side. the left-hand side of the wall is more positive, the right-hand side of the wall is more negative. The same thing is actually going to happen to the balloon. The balloon is going to sense that, hey, this left side, this side of the wall near me is now negative. What do you think all those charges are going to do? They're going to, as much as they can, even though the balloon's an insulator, move towards that side. So we've actually polarized the balloon as well. The left-hand side of the balloon is more positive because there's not as many negatives over there. And we're not saying all the electrons move, but a good chunk of them do. The right-hand side is where all the electrons are congregating. That's the more negative side. So both the balloon and the wall are polarized. We know this because the charges have separated. But there has been no transfer of charge. The wall is still electrically neutral. The wall still has an equal number of positives and negatives, protons and electrons. The balloon started off negative. I had 7 extra electrons, 7 little negatives in here, and I don't know if you can see them all, but they are still on the balloon. There was no transfer of charge at all. All that happened was each object now has a distinct positive side and a negative side due to the influence of those charges. If I were to take the balloon away from the wall, everything would go back to normal. Everything would go back to like this. Now, I want to show you real quick an example of charging, or not charging, but polarization. And I can show it to you with this little demonstration that you can actually do at home. So, aluminum can polarization. You can do this with like a soda can. Okay? Let's show the charges on the soda can. So you see a whole bunch of negatives here, and I think they're just covering up the positive charges. So this soda can is actually neutral. Let's bring it, oh, okay, you see them there now. So let's bring a glass rod over here. So take a look at what's happening here. The glass rod has a positive charge to it, so it's been charged already. And look what that's doing to the negative charges. It's attracting them. They are moving towards that positive glass rod. And actually, the closer I bring it, the more that they seem to congregate. So this is now polarized. The bottom side of this is more positive. The upper side of the can is now more negative. If I move this around, I can actually move the can because of the electrostatic force of attraction between the rod and the charges in the can. Even though the can is neutral, it's not losing any charges. Okay? See? The can is still neutral, but it has been polarized. I can do the opposite with a rubber rod. Rubber rod is negatively charged. That's going to repel the electrons to the outside. So right here, you can see that we have a negative charge on the bottom of the can, positive charge on top. But again, if I get rid of the rubber rod, guess what? It's still neutral. No charges have been transferred. But when that rod, or when either rod, the glass or the rubber rod, are there, there is a polarization. Oh, cool, I can bring both of them there. I can kind of make them do all sorts of different weird stuff. Excellent. Anyway, that's a little bit about polarization. We can polarize an object, and here you can see it's really polarized. Polarization just means take an object, don't touch it, but split the charges up in the object so that one side is more positive, one side is more negative. Polarization is key when we are looking at creating a charge on an object. And by creating a charge, we mean making it so that an object has a charge, going from neutral to having either positive or negative charge, or changing the amount of charge. Polarization is usually key for that, at least for some methods. So charge can be, giving an object an electric charge can be accomplished in 3 different ways. And again, what I mean by that is objects obviously have electrons and protons and neutrons. They're made up of those. Giving it a charge means giving it a net charge, making it so that the overall object is not neutral. The first type of charging is the simplest. We're going to talk about charging by friction. If you've ever rubbed your feet over a carpet and then gone to shock someone, you have charged yourself up by friction. You just got to rub 2 objects together. One of the objects will automatically grab electrons from the other object. Electrons will leave one object and go to the other one. The key here, as we've implied before, is that the number of electrons gained by one object is equal to the number lost by the other object. And this is known as the law of conservation of charge. We've looked at conservation of momentum, we've looked at conservation of energy. Both of those ideas were that in given situations, the total momentum of a system or the total energy of a system remain the same. Law of conservation of charge just says you can't just create charge out of nowhere, okay? If there was a certain amount of charge to begin with, the certain amount of charge has to be there at the end. It could have changed places, it could have changed objects, but you can't just create charge out of nothing. Let me give you a little drawn example here. We're going to have an originally neutral rubber stick. Okay, and I know it's neutral because I'm going to put equal numbers of positive and negative charges on there. And we're going to have a neutral piece of fur. And that's also going to have equal numbers of positive and negative charges on there. Okay. Now, did I have to draw 4 of each kind of charge? No, I could have drawn 5 of each kind of charge, but the key would have been still that there's equal numbers. Now, if I rub these two objects together, if I rub the stick on the fur, what will happen is the stick, due to the type of material that it's made out of, and you don't have to know this part, but electrons are going to transfer from, or they're going to get picked up by one object and taken from the other one. The stick will actually take electrons away from the fur. So it ends up looking like this. Okay, the positives are going to stay in about the same place. Okay, remember, because they don't move. But we're going to pick up some electrons off of the fur. So now there is 1, 2, 3, 4, 5, 6 electrons, 1, 2, 3, 4 protons. My negatively charged stick, because there's more electrons than protons, has a charge of negative 2e, negative 2 elementary charges, 2 more electrons than protons. What does that mean for my fur? Remember, the positive charges don't move. If the stick gained 2 electrons, then the fur must have lost those 2 electrons. This now has a charge of 1, 2, 3, 4 protons, only 2 electrons, positive 2e. And we could convert that to coulombs if we really wanted to. So now we have a negatively charged stick and positively charged fur. Okay, that's how we can create a charge by friction. And I can show you a quick little example of that. Oh, where is it? Here we go. All right, I'm going to start this simulation again. All right, so take a look there. Rub the balloon on the sweater. What's going to happen? The balloon becomes negatively charged, and what that means is that the sweater must have become positively charged. The balloon took those negatives from the sweater. That means the sweater now has a lack of electrons, it's positively charged. The balloon has more electrons, it's negatively charged. The balloon seems like it's gained 7 electrons. The sweater must have lost 7 electrons, so it now has a charge of plus 7e. Balloon has a charge of negative 7e. That's a very basic type of charging. Now what we're going to do is we're going to look at charging by conduction. Now, you've talked about conduction before in other classes, such as heat conduction. It's heat transfer by objects simply touching each other. What we're going to do for conduction is you take a charged conductor. Remember, conductors let particles move around very easily. You touch a charged conductor to another charged or uncharged conductor. Electrons will always travel from the more negative conductor to the less negative conductor. Okay? If we're talking about how much negative charge there are, they go from more negative to less negative. Even if both objects have a positive charge, they go from more negative to less negative. So that would mean the less positive one to the more positive one. If the two conductors are identical, this flow of electrons, for which another name is current means flow of electrons, that's going to be important in a few weeks, will happen until the two objects have the same charge. It doesn't even have to be two objects, it could even be three. If the conductors are identical, the flow will happen until the objects have the same charge. Okay? Now, I think I can also show this on the simulation. Here's what we're going to do here. We've got a balloon, and we've got our objects. Notice that I can polarize each object by bringing the balloon around. I don't know why it's jumping so much. That's kind of annoying. I can polarize each object by putting the balloon there. I can split it up into positive and negative sides. Can do the same thing to the other one. If I take the balloon away, then the objects more or less go back to neutral. But I'm going to put the balloon up there. And just so that we can get these objects having different charges, I'm going to polarize the object. Okay, and now look. So most of the charges are now on that one object. And we're going to come back to this part later. I'm going to get rid of the balloon. And look at this. I have an object that is positively charged. I have an object that's negatively charged. -8, +8. I'm going to touch them together and watch what happens to the charges. These are identical conductors. What should happen is we get some flow of electrons back to make this a little bit more even. Now what should happen, and this is just an error with the simulation, is it should snap back to 0. Okay? Both objects should snap back to being completely, both objects should snap back to becoming completely neutral. I'm going to do this again, one more time. We're going to bring the balloon over here. We're going to polarize it. We're going to induce a charge there. Again, I'll talk a little bit about charging by induction in another video. I'm going to get rid of the balloon, and I'm going to do something that I will, again, explain a little bit later. Okay, 5, 4, 3, 2. There we go. Let's get rid of that. So now what I've done is I've created charges that it's not even the same amount of charge. And I'm going to charge these by induction again. One of these objects has a charge of -8 E, the other has a charge of +2 E. What you could do is you could try and guess as to what is going to happen in terms of the total charges. We're going to explain it in a little bit, but try and guess as to what's going to happen. If I go and move this -8 over to the +2, we know that they're going to flow from more negative to less negative. More negative on the left-hand side, less negative on the right-hand side. 8 and +2. The way this should work, and you see some flow happening already, and let's see, let's do this. Notice that they both ended up with a charge of -3 E. And there's a pattern to that we're going to see in just a second. Okay? Let's do some examples so I can explain in a little bit more depth. A metal sphere with an excess of 8 electrons comes in contact with a metal sphere with an excess of 4 electrons. What will happen? So here's the one with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. This is very clearly going to be the more negative one. The other object has only 4 electrons. This is less negative. We're going to touch them together. That's how conduction works. As we touch them together, what's going to happen is some of the electrons are going to flow to the other object to try to balance out the charges. Okay? They're going from more negative to less negative. Electrons move to balance charges. What ends up happening is over time, the electrons will keep flowing until we get objects with equal charges. In this case, we had -8E and -4E to start off. If we take one electron from the more negative, put it over here, we now have -7 and -5. take another electron, we'll have negative 6 because this will have lost 2. This will be negative 6 as well because it gained 2 electrons. So what ends up happening is we end up with 2 objects, even once we separate them, with equal charges. Equal negative 6e charges at the end. That's a very basic example of charging by conduction. A more common one might be something like this. A metal sphere with a charge of positive 3 times 10 to the negative 6 coulombs comes into contact with a metal sphere with a charge of negative 5 times 10 to the negative 6 coulombs. What will happen? So in real life, it's much more common to have big amounts of charge. Remember, a coulomb is a very, very big amount of charge. We can still figure this out, we just have to go through a couple different steps. Here's our first one. It has a charge of plus 3 times 10 to the negative 6 coulombs. Here's the second object, negative 5 times 10 to the negative 6 coulombs. If we're labeling, okay, more negative, less negative, or this has an excess of electrons, this has a lack of electrons, this one is more negative, and this one is less negative. That's not what I wanted. Okay. Let's actually take a look at that simulation one more time and see if we can guess as to what happens here and what the rule is. So let's see. I'm going to set this up real quick for us. Okay, there we go. Go to the balloon. And okay. So, same thing that we had from before. Negative 8 and positive 2. And if you remember, what happened was that they end up both with negative 3. And so we could count this out. We could say that, okay, so one electron's going to go, once they touch, one's going to go from here to here. That'll be negative 7 and positive 1 because it's getting more negative. And then it'll be negative 6 and 0 because this one will be neutral then. And then negative 5, negative 1, negative 4, negative 2, negative 3, negative 3. There's a way to determine that without actually seeing it happen. Let's find the total net charge that's in the system right now. We have a charge of negative 8 on one object and a charge of positive 2e, elementary charges, on the other object. The net charge would just be adding those charges together. Negative 8 plus 2 is negative 6. There's a total charge of 6 extra electrons in this system. Okay? Negative 6e. If we want the charges to be equal, we need to split that negative 6e into 2 objects. Negative 6 divided by the 2 objects we need to split it between so that they each have an equal number of extra electrons is negative 3. And lo and behold, that is exactly what happens here. We can apply that to this problem. When these 2 objects touch, electrons are going to go. Electrons flow toward the less negative. In this case, less negative is the same as more positive conductor. How do we know exactly what charges they'll come up with? What we did last time was we added the charge up. So add charge including the sign. And then we divide the net charge evenly between all objects. So 3e negative 6 minus 5e negative 6 gives us 1, 2, 3, 4, 5, 6 negative, okay, so let's see here. 3 times 10 to the negative 6c minus 5 times 10 to the negative 6c is negative 2 times 10 to the negative 6c. Negative 2 times 10 to the negative 6c divided by 2, because there's 2 objects, gives us, divided by 2, negative 1 times 10 to the negative 6c. That is the charge that's going to go on both of these objects. and those charges are equal. That's the basics of charging by conduction. You should always get the same charges on each object at the end. It's up to you to figure out what those charges should be. If it's single, like electrons moving around, you can almost kind of guess and check. You can say, okay, move this over here, move this over here. If it's big amounts of charge, this would take forever if we were doing this method. You simply add up the total charge, and then you divide by how many objects there are. And don't forget, if it's negative charge, you have to account for that. Put a negative sign in when you're adding. In the next video, we'll talk about charging by conduction, and we'll talk about electroscopes. Talk to you later.